How to write your own Oxford interviews questions for chemistry. So, how do you go about writing an interview question? One good method is to take your inspiration from past undergraduate papers, although if you don't have access to these, your old notes could work equally well. Here, I'm going to talk you through how I construct questions from past papers, using inorganic, organic, and physical chemistry papers. First, let's look at an inorganic chemistry paper. These are the easiest of the three to adapt into interview questions because you tend to need less background knowledge to approach a given question. Here I have the 2016 third year paper. Let's look at question 1B1. I should probably note here that this question is on the electronics of solid state materials, which is my area of expertise. Explain all the following observations. Silver bromide is a poor conductor of electricity at room temperature. The electrical conductivity of Ag1-2x, CdX, Br initially decreases with increasing X, reaching a minimum at X is about 0.04, and then increases as X increases, eventually exceeding the conductivity of pure silver bromide at X is about 0.13. So to adapt this, I would probably write a starter question to get the candidate thinking about structure. Question: what do you dope iron with to make steel? The answer is of course carbon. There are lots of other things in steel too, like molybdenum, nickel, chromium, manganese. Question: why are carbon and small amounts of other metals added to iron? Or I might phrase the question in a devil's advocate kind of way. Question: so, is steel just dirty iron that engineers couldn't be bothered to purify properly? If they say yes, take them back to the blast furnace and how iron is extracted. This may lead them to conclude that carbon is a contaminant, but it should be clear that metals are deliberately added. If they don't guess, let them know that these are added to make steel harder or more corrosion resistant. Question: on an atomic scale, how does adding other elements improve the hardness of steel? This is a hard question, and the candidate may need lots of clues and guidance. In general, even if you say on an atomic scale, applicants will try to answer without referring to chemical structure and hope you don't notice them doing this. Yes, really. I suggest asking them to explain malleability and ductility, mentoring differing atomic radii. Encourage the candidate to draw their ideas on paper as much as possible, especially if they are nervous or lack technical vocabulary. The candidate should come to the conclusion that differently sized particles disrupt the regular arrangement of atoms in the solid metal, preventing them from easily sliding past each other under an applied force, and so leading to the macro property of hardness. You can use this result to conclude that a metal is actually much like a crystal lattice. This question is already long, and you can stop here if the candidate is struggling. However, if you want to push an able candidate, you can move on to the part in the paper. Question: silver bromide is a poor conductor of electricity at room temperature. However, it can be doped with small amounts of cadmium to improve its conductivity. Can you explain what doping is to me, please, and how it improves conductivity? Here, look out for the candidate only answering part of the question you asked, and ask it again exactly the same way if they don't. They will need to explain improving conductivity in terms of electrons and/or cadmium ions supplied by cadmium to the solid. You may ask them to draw out the half reaction and identify a plausible oxidation state for cadmium. Question: sodium chloride, common salt, conducts when molten or dissolved, but not when solid. Why? The candidate should explain the importance of free movement of charged ions. Question: so why does doping silver bromide, a solid, with cadmium improve its conductivity then? The candidate here is expected to make the distinction between free-moving ions and electrons with comparison to metal bonding. Question: actually, whilst doping silver bromide with a lot of cadmium improves its conductivity, doping it with only a small amount reduces it. Can you explain why? The candidate is unlikely to have heard of or draw on band theory, so you're looking for the idea of complete incomplete subshells or bonding orbitals. They should explain that unfilled shells can consume cadmium's released electrons until they're full, and then they're free to carry charge through the solid, or that unfilled orbitals, as they go from half full to full, leave fewer unpaired electrons that can jump to other orbitals. This second explanation draws on their A-level knowledge of transition metals. Beware giving clues that not all candidates will have covered colour chemistry and the d orbitals yet. And that's it. This question would form the bulk and second part of the interview for me. I would start with a quick maths question, then a short easy question to put them at ease, then do this. I'd also have a spare lying by. A good example is question 5 of this paper. Here's a table of data. This is an easy question to ask as you pretty much say go and make the candidate do all the work. It's also intimidating, so don't ask it right at the start of an interview. You can let it go on for 10 minutes or use it to fill a spare 2 or 3, depending on how much you push the candidate. It goes like this. Question. Here's a table of the rate that the water molecules coordinated to a metal ion swap with other water molecules in the surrounding solution. What information can you extract from the data? Points include: lanthanides form metal complexes too and have more than 6 water molecules around them. They may attempt to name this or state the shapes they form. Mention of size trends going down the periodic table groups in the metals and how this affects bonding strength, and type if you push them to discuss contribution of covalent character. If supplied with the periodic table, lanthanide coordination increases from 7 to 8 across the row. This could be accompanied by discussions of size trends and the observation of the lower charge on europium. Overall charge, its effect on charge density, and how higher charge density leads to stronger bonding, and this makes bond breakage harder. No entropic contribution or driver, and no enthalpic contribution or driver, as it's the same thing exchanged for the same thing, and statistics only. More statistically likely to swap the water molecules when there are more of them. This could be followed by dividing the numbers by the number of water molecules present, and commenting on how it might be a power effect rather than a multiple. Mention of possible competing reactions, such as deprotonation of water molecules by other water molecules, and how the acidity of a metal can be assessed and how this contributes to the effect. And lots more. When it comes to organic chemistry, question 1 Part A is usually a goldmine. These questions are designed as starter questions and ask undergraduates to apply one principle over and over again. If you teach your candidates this principle with a bit of guidance, they should be able to approach some well-chosen examples equally well, and you can pretty much ask the question given in the paper. For example, question 1 Part A of this paper asks you to find some reagents to create the following synthons. I would ask this question by introducing the term synthon and giving an example. Question. I'm now going to introduce you to the term synthon. This describes the effective charge you could imagine on a reactant after a good leaving group has gone. For example, a double bond could be positive at one end and negative at the other, so when hydrogen comes along, one end donates electrons to snatch a hydrogen, and one end accepts electrons to receive a hydrogen. I'd then ask what leaving groups you could attach to a carbon to give certain synthons. I would use synthons based on 2 and 6 here, but I would simplify the ketone to acetone and do positive and negative versions of each. I'm looking for deprotonation under basic conditions, a carboxylic leaving group, a halide leaving group but not a hydroxyl or amine, and then I would use cues and prompts to get the suggestion of a group 1 or +1 oxidation state metal. I would follow up the question by asking what was unusual in what they saw in this organic chemistry question and expect them to comment on organometallic bonding. Another question is taken from question 5. It asks for examples of enantio, regio and chemoselectivity. To transform this into an interview question, I would ask if they had heard of any of these and write them down so they could see the words. They should have heard of enantio selectivity in the context of biological systems, although you may need to tell them it's the same as optical isomer selectivity. I would expect their explanation to include drawing enantiomeric pairs and prompt them to do so if they don't. You can then ask them to guess what they think regioselectivity and chemoselectivity are by decomposing the names and thinking about what other kinds of selectivity can exist. You can call them position selectivity and functional group selectivity to help if necessary. I would then give them 2 examples, Markovnikov and anti-Markovnikov regioselectivity and the selective reduction of a ketone in the presence of a carboxylic acid group with sodium borohydride, and ask them to explain the chemistry and decide which of the 2 new selectivities is being shown. They should have some familiarity with these reactions, except boron addition across the double bond, but are unlikely to have encountered sterics, so encourage them to talk about it. For a good answer to this question, I'm looking for a candidate who can structure their answer, gather evidence and then make decisions based on it, and have confidence in the quality of their guesswork rather than simply aiming for the correct answer or trying to fluff their way through. Here's another organic question. Question. In the presence of potassium hydroxide, phenol reacts with this reagent to produce the product shown, water and fluoride ions. Can you draw arrows to suggest how the reaction works? Here you're expecting them to deprotonate the phenol and perform an SN2 with the trifluoride. Question. This is a good mechanism and exactly what we'd expect, but it turns out the reaction actually goes a different and rather strange way. First, can you tell me which hydrogen is the most delta positive? They should choose the one on the trifluoride and justify it in terms of electron withdrawing fluorides. Question. In that case, why wouldn't the hydroxide ion deprotonate here? They should conclude it does, not least because you've told them a different mechanism is at work. Question. Tell me about the strength of carbon-fluorine bonds. Once they've concluded that they are at least weaker than carbon-hydrogen bonds, show them the formation of the carbene and ask them to comment on the number of bonds to carbon. This should be compared to variable valencies in nitrogen, sulfur, phosphorus, etc., and although you may need to provide examples, ask them to provide some too. An interested candidate may ask why, and you can reward their interest by briefly explaining octet expansion. Question. The carbene can both donate and accept electrons to insert itself into an existing bond. Bearing in mind the product of this reaction, can you indicate which bond it inserts itself into and draw the curly arrows? Physical chemistry papers are often much less usable because they involve new notation. Some of the first year papers do however offer quantum mechanics questions that are basically just differentiation and integration. Most of my physical chemistry questions come from first year maths papers, although I also derive them from A-level concepts. So I'm looking at this question from the start of the 2016 third year paper, but I'm going to use it as inspiration to talk about the underlying principles, not show them a table of data. Question. What happens when light interacts with bonds? We're looking for the conclusions of light absorption and energy and momentum conservation. Energy and momentum are conserved as bending and stretching. I would follow this up by asking them to draw the possible bond rotations and vibrations for a water molecule. All of them. Watch out for symmetrical alternatives. It may be useful to hint that stretching also involves compressing. Question. Can you tell me what a dipole is and draw it on the molecule of water? Which bends or stretches do you think involve changing the dipole moment? Explain to them that IR spectroscopy is a measure of a change in the dipole moment of a molecule under infrared radiation. Finish up by asking them to evaluate the effect that not all bends or stretches appearing on the IR spectrum might have on substance identification. You are looking for a more in-depth analysis than "it may make it harder." Get them to say why and suggest at least 3 ways.